Okay, so last time we were talking about chapter three, and we were talking about some energy changes that occur when the electrons transition from one energy level to the next. You could use that Rydberg's equation that we saw, which change in energy is equal to minus 2.18 times 10 to the minus 18 joules, which is essentially the Rydberg constant. 1 over n squared final minus 1 over n squared initial. Remember, n is basically the principal quantum number. It's basically the energy level. And what we have here is, again, an equation that we could use to basically figure out how much energy is either going to be released by the atom if the electron, again, is going to go from a higher energy level to a lower energy level. That amount of energy will be released by the atom, or if it will be sort of absorbed by the atom. And in that case, that is the situation when our electrons are going from a lower energy level to a higher energy level. They will gain a certain amount of energy, obviously, to do that. This equation, which is the change in energy, does sort of tie into the same energy equation that we saw before. So if you have a problem like this, where obviously you have just the energy levels given to you of an electron transferring, you can figure out for example, the frequency of that energy coming off by tying that in. So basically, this is equal to h times v, or the frequency. And obviously, this is still the hc over the wavelength, which means you could also, if you have sort of that energy level transition, you can basically tie that to our wavelength sort of version of it and figure out the wavelength of energy or light that's coming off basically as this electron is doing this transition. Um, that obviously, in conjunction with our regular sort of frequency and wavelength equation, allows you really to figure out all those things, much like the lab we did the other day. You basically just, from the energy change of the electron, can figure it out. A couple of things that we talked about that you do want to be careful of is signs. So as we talked about energy, you're all good if you do get a positive or a negative number, and you should keep the sign for energy as either positive or negative, depending on which one did you get. Again, because that's really important for energy, it basically tells people what type of process is happening here. Is it an exothermic process, which will give you a negative value for energy, which means energy will be released? Or is it an endothermic process, which means, again, energy will be absorbed? And that is typically, in terms of energy values, usually results in positive numbers. So you definitely want to make sure that you keep the energy either positive or negative, but also really important if you're going to tie it into some calculations like we did in that lab, where you're going to calculate something like frequency or wavelength. Those guys, again, do need to be positive numbers. So what we typically do is just, if it happens to be a negative value for energy, we just make it positive when we go into those calculations. The number is going to be the same. So, if that electron, for example, went from like the third energy level to the first, and it dropped from the third to the first, or if the electron went from the first to the third, the actual amount of energy, if you will, or the number for the energy will be the same no matter which way it's going. Just the sign will be different depending on which way it's sort of going. And again, you should always get a positive value for E, as I mentioned before, if you're going from kind of lower energy to higher energy levels. And you should get a negative value if your electron's kind of transferring downward. Any questions on that there? Yeah. For energy, yeah. So just in general, pretty much all energy sort of values that you calculate, if you end up with a negative value, that usually implies that some type of exothermic process happening. And if you end up with a positive one, that usually means something is basically being absorbed. Other questions? Yeah. Hmm. Yeah. So if your question is, if it goes from a low to a high, the amount of energy is really for a particular element will be the same, as it goes from if it went, say, from the first energy level to the fourth, or if it started out of the fourth and went to the first, it would really be the same amount of energy difference. Again, the actual value, the amount of energy would be the same. The difference is whether or not the atom is gaining that energy to allow the electrons to go from a lower energy level to a higher, or if the atom is going to sort of release that energy so that the electrons could relax back down to a lower state. But yeah, same idea, going upwards or going downwards. You know, depending on how many energy levels it goes, would correspond to, you know, as we tied it to maybe a longer wavelength, shorter wavelength, depending on how much it's traveling. Other questions? All right, so we left off on this example, which I said to do at home, which I'm sure you all did. Good following instructions. All right, so let's go through it here and see what we end up with. So this is very much like the lab we did the other day, and we got some transitions that are happening here. So for A, we have our electron that is going from the fifth energy level to the second. So once again, in this case, we are only given really the energy levels. So we can use, obviously, the Rydberg sort of equation there to calculate what's happening here. So we got 2.18 times 10 to the minus 18 joules. We're going to go 1 over our final squared minus 1 over our initial energy level squared. So popping that in here, we'll go minus 2.18 times 10 to the minus 18 joules. 1 over our final. So again, our final is the second energy level there. So that's going to be 2 squared, which would be 4. Minus 1 over our initial, which is going to be 5 squared, which would be 25 in that case. So once again, here we'll pop that into our calculator correctly, hopefully. 1 divided by 4 minus 1 divided by 25. And we're going to times that by 2.18 to the minus 18. And we will end up with basically some energy here. We'll call it 4 point, we'll go a couple decimal places here, 58 times 10 to the minus 19 joules in this case. Obviously, at this point, that's really the only thing I could calculate based on information given to me, which is obviously our energy levels. But that's okay, because as we talked about, we can basically figure out all the other sort of information from that. So why don't we do that? So we can, right off the bat, because we just figured out the energy, we basically can use our E is equal to H times the frequency, and we could really get the frequency from that. We're going to divide this to the other side, and that'll give us that the frequency is equal to E divided by H. And once again, here, H is one of those constants, which is Planck's constant. And that is our 6.63 times 10 to the minus 34 joules times seconds. And if we pop our number in there, frequency is going to be our energy that we just calculated. And by the way, this should be negative, because I forgot the negative there, but that should be negative 4.58 times 10 to the minus 19. But obviously here, when I'm going into this calculation, we do want to get rid of the negative, but we should keep the negative for our energy up there. And it does make sense that it is negative value, because again, our electron's going from a higher energy level to a lower, so got to give off that energy. So again, an exothermic process here in terms of the energy. We're going to divide it by our 6.63 times 10 to the minus 34 joules times seconds. In this case, our joules are going to cancel. That is going to leave us reciprocal seconds. And bless you, that will get us 6.63 to the minus 34, dividing the energy by that number will give us a frequency here of 6.90 times 10 to the 14 reciprocal seconds, which obviously is also a hertz. So we have our energy and we have our frequency, and now we can actually calculate what it was looking for, which we could have also done and got the wavelength by using this equation as well. So we could have just jumped right in there and kind of used that equation and got the wavelength. But I feel like calculating everything here today, so why not? So we will go with our wavelength here. And really at this point, since you do have the frequency, you have two options. You could use this formula to get to the wavelength, or you could use the C is equal to the wavelength times the frequency as well. So you do have, at this point, since I did get the frequency, a couple of options. Yes. When you are calculating the wavelength or the frequency, because when you calculate wavelength or frequency, they do need to be a positive number. For the energy, you should keep it either as a positive or a negative value, depending on which one you get. But you definitely want to turn it into a positive value when you're calculating wavelength or frequency. So like I said, you do have some options here as to which one you want to do. So why not go old school here? And we'll do wavelength is equal to C times the frequency, or divided by the frequency, by dividing that to the other side. And you will end up with 3 times 10 to the 8 meters per second divided by our frequency 6.9 times 10 to the 14 reciprocal seconds. In this particular case, our seconds will actually cancel each other out, and we will end up with here, we'll go 4.34 times 10 to the minus 7 meters. I counted that right. 1, 2, 3, 4, 5, 6, 7. And if we wanted, for example, nanometers, we could convert that like we did in the lab or type of thing, since it is looking for maybe what color of light it might be. And we could do our 10 to the minus 9 meters is a nanometer, and we will end up with 434 nanometers in this case, or meters, whichever one you want to give it in. Any questions on that one there? All right, so wavelength here, I'll put it up here, it's just a little low there, 4.34 times 10 to the minus 7 meters, are 434 nanometers in this particular case. All right, let's take a look at the next one, and why not? Let's just solve for everything here so we can kind of see what's going on. We got an electron going from the 4th energy level to the 2nd. So on this one, we're going from 4 to 2. So once again, we could use our equation to figure out our energy, and we'll go with our Rydberg's equation here. And again, minus 2.18 times 10 to the minus 18 joules, 1 over our final, which again is 2. So we're going to square that. That's going to be 4. Not equal, but minus. 1 over our initial, which is 4, also going to be squared, which will be 16 in this case. So taking 1 divided by 4 minus 1 divided by 16, then times it by 2.18 to the minus 18. The right thing. It's going to get us here, looks like maybe 4.0. 4.09 times 10 to the minus 19 joules. Again, it's going to be negative. And also makes sense, once again, here we have an electron going from a higher energy level to a lower, so it doesn't need to give it off. If we're going to go for the wavelength here, we again could use this equation at this point, which is our hc over our wavelength. We're going to multiply that to the other side and divide that back over. And that would essentially give us the wavelength is equal to hc divided by the energy. Both h and c are constants, so you always have that available to you. So you basically just got to pop those guys in. So 6.63 times 10 to the minus 34 joules times seconds. And our speed of light, again, whichever number you like to use there. I'm going to go with 3 today. And we're going to divide it. Once again, here we are going to turn our energy value into a positive number, so we don't end up with a negative wavelength. And at this point, the joules will cancel, the seconds will cancel. We will be left here with meters as our units. And we want to go 6.63. We definitely want to be using our exponent button as we've talked about when we punch these in. And we're going to times that by speed of light divided by our energy here. And that's going to get us about 4.86 times 10 to the minus 7 meters. And again, if we just want to compare with nanometers, 10 to the minus 9 meters is a nanometer. That'll give us something like 486 nanometers in this case. And any questions on that calculation there? Yeah. Yeah. Because originally I was supposed to tell you to solve for everything, I didn't, so it's just in my head to do that. But really, the question is only asked for wavelength, I think. But while we're here, good practice. We'll just solve for everything. But really, probably because I was supposed to tell you to solve for everything. That was probably my bad. But here we'll solve for the frequency as well if we want the frequency. And at this point, we really again have two options. You know, which one you want to use here to get to the frequency. So again, we can use this guy here since we do have the wavelength. So we'll solve for the frequency, which will be c divided by the wavelength. Remember, though, obviously, if you choose this version of it, you definitely want to make sure that the wavelength's in meters, so everything cancels out with that speed of light. You would not want to use the nanometers in this case. So 3 times 10 to the 8 meters per second divided by our wavelength. Again, using our meter number there. That way the meters will properly cancel out and leave us with our frequency here of, looks like 6.17 times 10 to the 14 reciprocal seconds. Yeah. Any questions on that one there? Yeah. If it's not specified, probably meters is fine. You could technically solve for whatever unit you want if it's not specified. So I would say probably common in this sort of chapter, meters or nanometers are probably common sort of ending units. A lot of times people will go nanometers, especially in that visible part of the spectrum, because usually they kind of look at the light in terms of nanometers. But technically, if it's not specified, you could actually use any unit you want in terms of the wavelength. Other questions? All right, last one on this one, a 3 to 2 conversion here. So our electron going from 3 to 2. Once again here, only thing we could start with is the energy. So 2.18 times 10 to the minus 18 joules. We're going to go 1 over our final, which is 2, and we're going to square it. So that's going to give us 1 over 4, minus 1 over our initial energy level squared, which will be 9. And that's going to get us here 2.18 minus 18. I should do that way. 1 divided by 4 minus 1 divided by 9. And then times it by 2.18 to the minus 18. Going to shoot us here a negative 3.03 times 10 to the minus 19 joules. Again, at this point, if you're going to probably just do what the question really asked, which is the wavelength, you would probably want to go into our E is equal to hc over the wavelength. Again, because you have the energy and the h and the c are both constant values. So here, solving for wavelength would be hc divided by E. Once again, multiplying that way and dividing that way. And popping in our numbers here, 6.63 times 10 to the minus 34 joules seconds. And our 3 times 10 to the 8 meters per second divided by 3.03 times 10 to the minus 19 joules. Once again, we are converting, obviously, our energy into a positive number so that we end up with a positive value for our wavelength. Obviously, just like we did here and previously, we are going to keep the negative here for our energy value, as that's important for energy. Also, electron going from higher energy to lower. So once again, we would expect our energy to be negative. Canceling out our units, once again, going to leave us meters here for our wavelength. So 6.63 to the minus 34 times 3 to the 8 divided by 3.03 to the minus 19. Going to get us, I believe, 6.56 times 10 to the minus 7 meters. And again, if you want nanometers, that's a super common conversion here. So again, like we did in lab, 10 to the minus 9 meters is 1 nanometer. So you're looking at about 656 nanometers in this case. And here, might as well, since we did it for the others, we'll solve for our frequency. So we can do this, or obviously we could also roll with that. So just to be different, we'll roll with that one in this case. So our E divided by H will equal our frequency when we divide that to the other side. And once again here, if we're going to use this equation with the energy, we again want to make sure we turn it into a positive number. So 3.03 times 10 to the minus 19 joules divided by our Planck's constant. Again, here, joules are going to cancel. When you divide the seconds on the bottom, that will become reciprocal seconds. And we will end up with here, looks like 4.57 times 10 to the 14 reciprocal seconds as our frequency. Is your question? Yeah. The question was, I think, which one was the longest wavelength? And here we see when we look at wavelength, we have 434 nanometers, 486, and 656. So the longest wavelength here is our 656. That also makes sense if you think about sort of our energy conversation as well. Our longest wavelength, right, was a result of this electron going from the third energy level to the second, kind of like one energy level change. Which is less energy than probably our shortest wavelength, which was over here, I believe, 434. Shortest wavelength had the longest transition, right? And also had the highest energy that was released in this case. And again, those are the relationships that we talked about earlier. Short wavelength, higher frequency, and obviously higher energy. Longer wavelength, lower frequency, and lower energy. Any questions on any of those calculations? All right. So we were talking about Bohr and Bohr's model, sort of the atom, and this sort of planetary model of electrons moving in these really nice orbits. And we know exactly sort of where they're located in a sense. They're in this orbit or they're in this orbit, and they're moving around the nucleus in these sort of pretty circles. What we're going to talk about here just briefly as we kind of move away from that is kind of moving away from Bohr's idea of the atom, as we talked about. As you kind of introduce more than one electron like we have in hydrogen, it doesn't sort of hold up very well. And this idea of we know exactly where a particle like an electron is and how it's moving, we do sort of move away from that to a more quantum mechanical type of situation where, as we will talk about, we don't really know exactly, you know, where the electron is or exactly how it's moving. And one of the things that sort of moved us sort of into that direction are really sort of reaffirm the idea that, you know, electrons and particles like electrons could have both sort of a wave-like function and also a particle-like function, was some work that was done by deBroglie. And deBroglie did a lot of theory about it. He actually didn't do any sort of experiments per se. They were later done by other people that actually kind of proved his idea right. And deBroglie sort of predicted that the wavelength of a particle is inversely proportional to its momentum. And because they're really small, the wave character of electrons are significant. So again, it's this idea of sort of the dual nature of light, that particles can have particle-like function, obviously, but they can also possess some wave-like function, and sort of vice versa. There's sort of wave-like function and particle-type function. And deBroglie came up with this equation for the wavelength of particles. And this is what is sometimes referred to as the deBroglie wavelength. And the wavelength here in meters is equal to h, excuse me, divided by the mass and times its velocity. Now, when we use this, we do want to be careful of some of the units here. And if we just sort of look at units here, H is joules times seconds. Up on the bottom here, we actually want the mass in kilograms, and the velocity here is in meters per second. And the way that we actually get everything here to sort of properly cancel out is we actually get rid of joules in Planck's constant. The good news is the number doesn't really change or anything like that, but we just kind of look at it as rather than joules times seconds. A joule is equal to a kilogram meter squared second squared. So if you have a joule, it is equal to that relationship, which means if you substitute that in for our joule here, we will end up with a kilogram meter squared second squared times an S up on top, divided by a kilogram and a meters over seconds. And now we have all the units that are going to kind of cancel out the way we want it. We have a second there and a second there. That's going to take out both of those seconds. We're going to have a kilogram that's going to take out a kilogram. And we got 1 meter that's going to take out 1 meter. And that is what's going to leave us with meters here in terms of the de Broglie wavelength. So when you're calculating the de Broglie wavelength, you will end up in meters. The good news is this H honestly is still the same number. It's still the 6.63 times 10 to the minus 34. It is still technically joule seconds. But again, by using sort of that definition of a joule, that is how we kind of get ourselves to meters at the end of it. So the deal here is when you're using this equation, there's really two things you just got to make sure of. You do have to make sure the mass is in kilograms, and very commonly people always want to kind of roll with grams, right? Because they think mass, we think grams. So you want to make sure you have the mass in kilograms. You also want to make sure that the velocity is in meters per second, again, so everything cancels out. You could be given the velocity in miles per hour or some other unit. You may have to convert it into meters per second so everything properly cancels out. So the proof of this sort of wave nature of an electron came a few years later when a beam of electrons would produce an interference pattern as if they were basically waves. And so if you remember, we saw sort of that interference pattern earlier on where you have kind of the light spots and the dark spots on the wall as the wave sort of function goes through it. So if electrons only behaved sort of as particles, there would only be really two bright spots. They would just shoot straight forward. There was no kind of wave function associated with it. But again, what they saw was this kind of interference pattern where you had a bunch of those kind of light spots and dark spots, as we talked about. Here, the waves adding to each other are subtracting from each other. Again, sort of showing that electrons, which is a particle, is exhibiting some wave-like sort of function as that sort of de Broglie sort of thought of. So why don't we try and calculate the de Broglie wavelength here? If we have an electron that is traveling 2.65 times 10 to the 6 meters per second, that is the mass of an electron, 9.11 times 10 to the minus 31 kilograms. So give a look in this particular case, if you're trying to calculate the wavelength of a particle, de Broglie wavelength is probably again, our wavelength in this case is going to be h times m times the velocity. We are given the velocity, and as I mentioned earlier, it is in the correct units that we need it in, which is meters per second. We also have the mass given to us, which is also in this case in the correct units, which is kilograms. And basically, Planck's constant is still Planck's constant. Again, we're going to use the relationship that the joule is a kilogram meter squared second squared. So really all we have to do is pop this in here, our 6.63 times 10 to the minus 34. I will use those units for the joule part of it. So kilograms, meters squared, second square. Once again, that is basically the joule part of it. We do want to remember that Planck's constant also is time seconds, so that's where the extra seconds come from. So we still have a seconds up there on top in terms of the unit that's being times, as what I just put here in parentheses is just the joule part of the units in this case. We're dividing by our mass, which was again in kilograms, which is good. And our velocity, which is also in meters per second, which is good as well, 6.5 times 10 to the 6 here, meters per second. Again, in terms of units, we're going to get everybody to cancel out right. So seconds, there goes squared seconds, kilograms, kilograms. 1 meter takes out 1 meter. Again, going to leave us with just 1 meter left. So 6.63 to the minus 34 divided by 9.11 to the minus 31. Sure. Try that with the number there. 9. And divided by 2.65 to the 6. Going to get us a deBroglie wavelength of about 2.75 times 10 to the minus 10 meters in this particular case. Any questions on that calculation? Yeah. Yeah. On which side? This one or? Yeah, so s to the minus 1 is 1 over seconds. So if you times that by the meters, you get meters per second. Is that what you're asking? This right? Yeah. So remember the minus 1 basically means 1 over it. So that's how the seconds are on the bottom there. Yeah. Other questions? All right, let's try one more here. Let's calculate the deBroglie wavelength for a neutron that is traveling 1 times 10 to the 2 meters per. Okay, so let's take a look. So again, we're going to use the same formula there, our h divided by our mass and our velocity. We obviously have our velocity given to us, and we do have our mass. Again, in this case, though, our units here for our mass is not the units that we need. Again, we don't really want to use them in grams, otherwise we're going to be off by a factor of 1,000. So there are 1,000 grams in a kilogram, right? Our 10 to the 3 grams is 1 kilogram, right? Same deal. So we'll do that conversion first just to get everybody in the proper units here. Minus 24 grams. We're going to divide by 1,000, basically. Grams are going to cancel, and we'll go, we got there 1.675 minus 24 divided by 1,000. Going to get 1.675 times 10 to the minus 27 kilograms in this case. Now we have our mass in the right units, our velocity in the right units, and obviously h is our constant. So we'll go with our 6.63 times 10 to the minus 34. Again, the joule part there are going to be kilograms, meters squared, second squared, times a second, divided by our mass there, 1.675 times 10 to the minus 27 kilograms. And our velocity of 1 times 10 to the 2 meters per second. And if we do all that good stuff there, I like my line should go bigger. There we go. 6.63 to the minus 34, 1.675 minus 27, and divided by 1 to the 2. That's going to get us here something with a lot of zeros. All right, so everything's going to cancel out here except for the 1 meter. And it looks like we'll get something like maybe 3.96 times 10 to the minus 9 meters. Or in your calculator, you might have a bunch of zeros and a 4 at the end because your calculator ran out of room, basically, and that'll be the same thing. Any questions on that there? So again, what deBroglie sort of demonstrated was things like neutrons and electrons, which are particles, do definitely have a significant sort of wave-like function. And you could obviously use his formula there to calculate the actual wavelength. So as I was mentioning, this is sort of moving us really away from Bohr's idea of, it's pretty, we know where everything is. We know how the electrons are traveling around the nucleus in these orbits. To this idea of really, we don't really know how a particle like an electron is really moving, or really where its location is at any given time. So we have sort of complementary properties. The wave and particle nature of an electron are complementary properties. And one of the main ideas of this is the more you sort of know about one of those sort of properties, for example, about an electron, the more you know about how it's actually moving, the less you know about, sort of its position and vice versa. And that brought us to Heisenberg and his uncertainty principle, which is this is the formula here for it. And we're not going to really use it to calculate too much in here. But again, x being the position, nu there being the velocity, and the uncertainty of those things. And again, the idea here is unlike the sort of Bohr model where like I know the electrons in an orbit, if I just kind of put my finger there, like I said before, it eventually has to come around right in the circle, and we can eventually sort of figure out, where it is, how it's traveling in these nice, pretty circles. And this is moving us away from that sort of idea to this sort of quantum mechanical idea of no, we really don't know how it's traveling. We really don't know where its location is. And again, the more you sort of have information about one, the less you know about the other. And for example, here is sort of the idea here. If you have an experiment to observe an electron, what we see is a single electron particle and no interference pattern. So we don't see the wave-like nature of things. And again, the more you kind of know about one thing, the less you could kind of observe the other sort of aspect of something like a particle here. So in this case, we could actually only kind of observe the particle nature of it. We're not able to also sort of simultaneously observe the wave-like function of it as well. And with that being said, electrons and their energy and their position are complementary to each other. So what we did is sort of move away from this idea, as I mentioned before, of I for sure know, like in Bohr's model, the electrons has to be in these orbits. They have to be circling around, to this idea of there's really some uncertainty as to how the electrons are traveling and maybe where they're located. And this idea is we do move away from sort of the idea of orbits like we had in Bohr's model to this idea of, the best we could kind of do is talk about probability and the probability of finding an electron in a particular location. And really, we move away from orbits to what are referred to as orbitals or atomic orbitals. And as we'll talk a little bit about, these are essentially just probability maps of like, there's a pretty good high probability in this part of the atom. You might find some electrons, and there's maybe a lower probability out that way that you could find them. Still have really no idea how they got there or how they're moving, but there's a good chance. Now, when we think about sort of the probability of finding electrons in a particular place, this is all based on what is sometimes referred to as wave function as well, which we're definitely not going to get into. But if you ever take physical chemistry, that's fun. Not really. But the idea of the atom, right, is we do have this positively charged nucleus, and ideally electrons are obviously negatively charged. So there is an attraction between the negatively charged electron and the positively charged nucleus. And you would imagine that your highest probability perhaps of finding electrons would be somewhere in that area near the nucleus, right? And as you sort of fan out from the nucleus at some distance, the probability of finding an electron is probably going to get a little bit less than it is if you're kind of closer to that positive thing. Absolutely does not mean you can't find an electron out there. It's just, you might have a better shot of finding one quicker, maybe near that positive charge. And that is essentially what atomic orbitals are. They are these sort of theoretical probability maps that do have shapes and stuff like that. And that is where we sort of think about where electrons are found in the atom. As we will see here, and as you may remember, there are some different types of orbitals like s orbitals, p orbitals, d orbitals, and f orbitals. And each of those, again, are these sort of probability maps. Now, Schrodinger did a bunch of these equations, these wave function type equations, that basically sort of characterize these probability maps. And the relationship of this is basically what is referred to as quantum numbers. And there are 4 different types of quantum numbers, and they really are the basis of these sort of calculations. And honestly, they are the basis of, why we have s orbitals on certain energy levels, why we have p orbitals on certain energy levels, why there's 3 p orbitals versus with s orbitals there's only 1 s orbital, and it's based on these type of quantum numbers. And we're going to talk about each of these individually and sort of what they sort of represent. But one of the quantum numbers is something that we've seen already, which is the principal quantum number. That is n. That is essentially, as we've been talking about, basically the energy level. There's the angular momentum quantum number, which is L. And there's the magnetic quantum number, which is m sub L. And we'll see it here on another slide coming up. But there's the spin quantum number, which is m sub s. And those are really the 4 quantum numbers. 3 of the 4 here are really related to sort of the orbitals themselves. The spin quantum number is more related to the electrons in those orbitals and sort of what happens to the electron in those orbitals. So let's talk about each of these and sort of understand sort of what they represent. And again, the principal quantum number, which is n, is again the energy level, is what you can kind of think of it. It is the different energy levels. N could have values of 1 through 7. And as we kind of talked about earlier, an n equals 1 is the ground state. That is, again, the lowest in energy. And it is obviously closest to the nucleus. And anything higher than that, as we also talked about, kind of n2 through 7, those are what are referred to as excited states. And again, those are higher in energy, further away from the nucleus. Now, for every value of n that you have, you can have basically a angular momentum quantum number, which is L. And L basically will have values of 0 to n minus 1. And we'll talk about what that means in just a second. But for every n value you will have an L value. What is really L? I'll be honest with you. L is the type of orbital you end up with. Is it an s orbital? Is it a p orbital? Is it a d orbital? Is it an f orbital? It kind of tells you basically the type of orbital there is on that particular energy level that you may be on. The next type of quantum number is the magnetic quantum number, which is m sub L. And it can have values that range from minus L to 0 to plus L. So if you had an L value that was a value of 1, you would have an m sub L value of possibly -1 to 0 to +1. Yeah, so negative value of your L to the positive value of L, all whole numbers running through 0 until you get basically to the other side. What does that basically tell you? To be honest with you, it tells you the 3-dimensional orientation of those orbitals in space. But really, you can also think about it like this. It tells you how many individual orbitals there are. So how many s orbitals there are, how many p orbitals there are on an energy level, how many d orbitals there are, or how many f orbitals there are. As I mentioned before, the spin quantum number, which is m sub s, only have values of +0.5 or -0.5. And that has to do with, for example, if this line represented an orbital, any individual orbital, you can only put in there basically 2 electrons. So any individual orbital can hold a maximum of 2 electrons. And if your electron is sort of going into the orbital first, it will spin in what is referred to as the positive direction, kind of if this arrow represents the electron, it's going to point upwards. And that is what is known as +0.5 spin. And if your electron goes in second, it's actually going to spin in the opposite direction. And it's pointing downward. And that is what is referred to as -1/2 in terms of the spin. So the spin quantum number is not too bad. It's either like +0.5 or -0.5. That's basically what it is. And the quantum numbers here, N, L, M sub L, and M sub S, is really the basis for something that you probably have done before, and we're going to talk about here in just a second, electron configuration. And again, what orbitals there are on each energy level and why there's no orbitals on certain energy levels, but they only begin on like the second and they're not there on the first. And this is really the basis of how we get to all those things. So as I mentioned, our quantum number of n is our energy level. And let's just talk about sort of what this means in terms of orbitals. Now, let's actually first talk about atomic orbitals just to refresh everybody's sort of idea here. And atomic orbitals, again, are those theoretical sort of properties or maps where we can find electrons in an atom. And there are basically s orbitals. And when we talk about s orbitals, let's just talk about quantum numbers here, or how we get to s orbitals. So the quantum number of n equal to 1 is the lowest energy level you could have closest to the nucleus. So if I have on the first energy level, a n is equal to 1, which means you're on the first energy level, our L value that is possible in this situation is values of 0 to n minus 1. So in this case, my n is 1. So 1 minus 1 is what? 0. So the only possible value you could have for L is 0 here on the first energy level. Now, what does the 0 represent? The 0 actually represents an s orbital. And that is why on the first energy level, that is where we see s orbitals, and there's only an s orbital found on the first energy level. There is no other orbitals that are possible to be found there. Now, if we do m sub L, it could have a value of minus L to 0 to to positive L. And obviously you can't have a negative L, a negative 0 or anything like that. So if your L value in this case is 0, the only possible value for m sub L is 0. And what that means is on the first energy level, I will find only an s orbital. And it will only be one type of s orbital is there. And in that s orbital, you could have a spin quantum number that's plus a half or minus a half. You could have an electron going upwards, or you can have an electron going downward. And what that means is when we get to the very first energy level, that is where we see s orbitals. They actually appear on every energy level. Yeah, so you will have s orbitals on every single energy level. Because, for example, if I went to n is equal to 2, what value of L can I have? N minus 1 in this case would be 2 minus 1, which is 1, yes. But it could have a value of 0 to n minus 1, which means on the second energy level, I have a 0, and I could have a 1 for the value of L. And as we just talked about, obviously the 0 here represents an s orbital, which means it's on the second energy level as well. And if you did that for all the energy levels, you will always hit a value of 0 for L, which means on every energy level, there is an s orbital that's happening. Any questions on that there? All right, so let's talk a little bit about s orbitals here since we sort of found them there. So as I just mentioned, the s orbital begins on the first energy level, and it's on all energy levels, yeah. And based on the m sub L of just 0, there is only one type of s orbital. And again, that one s orbital on any energy level could hold 2 electrons. So for example, on the first energy level, that is what is known as a 1s orbital. If you go to the second energy level, that is what is known as a 2s orbital. Yeah. Go to the third, it's a 3s, and a 4s, and a 5s, and a 6s as you continue up the energy levels. S orbitals are basically spherical. They're kind of circles, if you will, probability maps in a kind of a circle sort of situation here. They basically are the same shape, but they do get bigger as you go from one energy level to the next to accommodate all the electrons that are basically coming in there. And it will continue to increase as the principal quantum number increases. So the only orbital we find on the first energy level are s orbitals, and obviously this is what an s orbital looks like as you go there.
An s orbital has a spherical shape with the nucleus at the center.
So again, that's basically just like a probability map, nucleus in the center, and again, probably high probability of finding an electron near it and lower probability as you sort of expand out. Again, the idea here with Heisenberg's uncertainty principle is don't exactly know where the electron is at any given time, don't know how it's traveling, just a probability of finding an electron. And again, as you can see here on this picture, much darker in the middle, kind of getting lighter pink as you get out there. And again, that's just a lower probability as you move away. Yes. That is correct. So it gets bigger as it goes from one energy level to the next. Again, you have to think about it as you're climbing energy level, there's going to be a lot more electrons to accommodate, right? So it's got to have a little bit, it gets a little bit bigger to sort of accommodate that. So here's that idea there as we go from the first energy level where we have our 1s to our second, where we have our 2s to our third, where we have our 3s. Again, the theoretical shape of this probability map gets larger and larger to sort of accommodate those electrons. Any questions on that there? Yeah. What's that? Yeah, so in the nucleus is where we have protons, which are positively charged, right? And neutrons as well, which have no charge. Yeah, so if you want to kind of envision where where the nucleus is, in the case of the s orbital, it's actually kind of like in the middle. I don't know if that showed up or not, but it's sort of in the middle there is where it's at. So there's also another sort of quantum mechanical idea that you could think of particles as having a wave-like function, and you could almost think of them as like a standing wave, like on a guitar string, right? You can pluck it, right? But the string's not going to go anywhere, right? But you just make a wave. So it's kind of anchored to the guitar, right? So that's sort of the idea here with our electron. It's sort of anchored to the atom through sort of wave function from that attraction to the nucleus. So it doesn't just hop off, right, and leave. Um, and usually where we find sort of what we envision sort of nucleus is like in the center are areas where there's like no amplitude, which is sometimes referred to as a node when you kind of look at it, is sort of where we refer to that. Yeah. So in terms of our next set of orbitals, if we think about what's happening as we go, say, to the second energy level, and we think about our quantum numbers with that, so we already have our n is equal to 1 as we did, which is our first. But now when we go to the second energy level, again, our n is equal to 2, which once again means that our L could have a value of 0 to n minus 1, which means, again, in this case, we could have 0, or 2 minus 1 is 1. As we just saw a second ago, that 0 for the L value represents an s orbital. When you get an L value that is equal to 1, that represents a p orbital. So that represents basically a p orbital. Now, for m sub L, which we go from minus L to 0 to plus L, obviously for each value of L, we could actually do this. So for our L that's equal to 0, the only option for our m sub L is 0. That is why we have basically one s orbital. We only have basically one s orbital on any level. Now, if my L value is 1, which also occurs on the second energy level, I could have a value for m sub L that runs from negative L, which would be negative 1, to 0 to positive L, which would be plus 1. That, by the way, is how many numbers? That is 3. 1, 2, and 3. And if you're not familiar, p orbitals come as the p subshell, which comes as 3 individual orbitals together. This is basically the 3 p orbitals, the px orbital, the py orbital, and the pz orbital. So this quantum numbers are telling us that when we have an L value of 1, which represents p orbitals, on any energy level that you have that, you should have 3 p orbitals that come along with that. And that's why we do have 3 p orbitals here. And obviously in each of those individual orbitals, they each can hold obviously 2 electrons for a maximum of 6 electrons if you filled up the 2p subshell or a p subshell. So the p orbitals in this case, based on quantum numbers, do not begin until the second energy level. That is where we first are sort of allowed to see p orbitals appear. They do appear after that on every energy level after that, but they don't start until you get to the second energy level. And there are 3 different p orbitals, which are arranged in 3-dimensional space, X, Y, and Z, like in math, right? You got a little coordinate plane there, X, Y, and Z axis, and they're in 3 different locations. Now, the theoretical sort of shape of a p orbital is a figure 8 or a teardrop sort of shape. As to like an earlier question, right around here where they kind of come in together is kind of assumed where the nucleus would sort of be. And the probability of finding an electron is you could find an electron in that lobe or that lobe of the p orbital. It could kind of theoretically be in those locations. And as I mentioned again, first energy level, the only thing we got going is a 1s orbital. We now get to our second energy level, still have an s orbital, but now based on quantum numbers, now we have some p orbitals basically starting to appear here. And again, there's 3 different types of them in 3-dimensional space. So here's again what a p orbital sort of looks like, kind of like a figure 8-ish.
The px orbital is in the shape of a figure 8 along the x-axis.
And as we were talking about, kind of the nucleus there in the center, electron can be found on either of those lobes. And again, you can see they're just in sort of different orientations, the px, the py, and the pz orbital. This would obviously be the pz on the z-axis there. And as you can see here, sort of the probability of finding an electron pretty good in this sort of area of these lobes. You can see it's much darker in that area. And that's again kind of closer to where we kind of see the nucleus. But again, as you can see, you could probability have still have an electron anywhere in that sort of area there. Now, when we move on to the third energy level, that's going to be our n is equal to 3. And with our n is equal to 3, when I go to L, what are the values I could have for L in this case? L could be 0, 1, and in this case, 3 minus 1 is 2. So what this is telling us now, when we get to the third energy level, we still have our s orbital there. We still have our p orbitals there. But now we get a brand new orbital that sort of shows up here on the third energy level. And that is a value of 2 for L, which is actually our d orbitals. So it's not until the third energy level that the d orbitals appear. And if I do my m sub L for d, my L is 2 in this case, that's going to be negative L to positive L. So negative L would be minus 2. Then they go minus 1. Then you go 0. Then you go plus 1. And then you go plus 2. How many numbers is that? That is 5. And that is why we have 5 different types of d orbitals that appear. These are all possible d orbitals that appear. And they form what I refer to as a subshell. So when we get to the third energy level, that is where we first start to see our d orbitals appear. And as you can see, each of those numbers represent each of those sort of 5 d orbitals. And In this particular case, you could also see that the d orbitals essentially look like two p orbitals kind of stuck together, basically. So same idea here, our lobes and our kind of nucleus here in the center and our probability of finding electrons. Although this one kind of looks like a donut with a p orbital through it, most of them look like kind of two p orbitals kind of put together here as well. So based on our sort of quantum numbers, on our first energy level, the only possible orbital we can have is a 1s orbital. On the second energy level, we could also have an s orbital, and again, that is where we start to see our p orbitals occur. On the third energy level, we had a 0 for L, which means, yeah, there's an s orbital there. We also had an L value of 1, which means there are p orbitals there. And we now have an L value of 2, which means there are now d orbitals that are present on that. So again, these quantum numbers are sort of the basis for, where the orbitals are, which ones are allowed to be on certain energy levels as we go through this. Any questions on that there? Now, here again is what our d orbitals look like, kind of the two p orbitals together.
Y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
We'll just kind of look at those here. Get the idea.
The 3dz squared orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z axis.
All right. Now, if we get to our fourth energy level, n is equal to 4, we will now have L values possible of 0, 1, 2, and 4 minus 1 is 3. And that means on the fourth energy level, just like we saw on some previous ones, we have an s orbital. We also have p orbitals on that energy level. We also have d orbitals. And now we introduce an L value of 3, which represents our f orbitals. So these are represented by f orbitals. And again, so n will have values of 1 through 7. L will basically be 0 to n minus 1. So basically all kind of whole numbers starting at 0 to n end at n minus 1. And once again, m sub L will run for every individual L value that you have. You could do an m sub L, and the m sub L will go from minus L to 0 to plus L. Also kind of whole numbers all the way kind of across there as you go through that. So with that being said, we could obviously do our m sub L for our 0, which would still give us 0 like our individual s orbital. If we did it for our 1, again, we would get minus 1, 0, and plus 1, which is our 3 p orbitals. If we did it for 2, minus 2, minus 1, 0, plus 1, plus 2, are 5 d orbitals. And if we now do our m sub L for our 3, we would have values of minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. That is how many numbers? That is 7. And that is the 7 different f orbitals that we have. So again, this is the basis for the existence of the 7 orbitals. And again, those 7 orbitals look like this down here, kind of couple d orbitals kind of squished together in a lot of cases. And again, the f orbitals do not begin until you get to your fourth energy level. So once again, building out sort of our energy levels, 1s on the first, 2s, 2p on the second, 3s, 3p, 3d, and now when we get to the fourth, also a 4s because we did have an L of 0, also a 4p because we had an L of 1, also a 4d because we had an L of 2, and here is where we have 1, 2, 3, 4, 5, 6, 7. I'll kind of squeeze it in. And that is where we start to see our f orbitals basically appear. So obviously we're building out these orbitals. These are again where electrons will be housed. Energy is increasing obviously in this picture as we're going upwards. and electrons do go in from lowest energy level to next. Just to finish up on here, if I had an n equals 5, possible L values would be 0, 1, 2, 3, and 4. So again, that's an s orbital. That's p orbitals. That is d orbitals. That is f orbitals. And clearly the fifth energy level has another one. What happens after f? It just goes alphabetical. So it's like G basically, and it just kind of continues alphabetical. We never see G orbitals or anything like that, right? Because we run out of elements there. Elements only get to F basically. But in theory, there are these other orbitals on the fifth energy level, the sixth energy level, seventh energy level, and the orbitals just basically go alphabetical after F if you get that high in terms of that. Any questions on that there? All right, we'll lay that up there.